So with function symmetry, the main properties we're looking at here are the potential for symmetry about the x-axis. I want to make the y-axis there, where you're talking about flipping it over horizontally. You call that horizontal symmetry in a shape. Then y-axis, something more like vertical symmetry. And then you have symmetry about the origin, which is a bit more like diagonal symmetry, where we have some pretty quick ways we can identify these in terms of the way the function behaves, in terms of function values. Where if we want to check for symmetry with the y-axis, we need to see if every point xy and negative xy are on the graph. So this would be something like you see with a very basic parabola, and you can check this by substituting negative x in for x. On the other hand, we get symmetry with the x-axis if for every xy we also have x negative y. So this is something more like the horizontal parabola, to be very lazy about a name there. But you check that by substituting negative y in for y and seeing if that doesn't affect the equation in any meaningful way. And then for symmetry with respect to the origin, we need both xy and negative x negative y, and you check that by, well, exchanging both x and y with negative x negative y and seeing if you end up essentially just with a bit of rewriting back where you started. So we've got our three cases here. As usual, what we're going to do is just get a little bit of practice so we can see how these tests actually work in the context of another example. So for this example, we want to determine whether the graph of y equals 1 minus x cubed has symmetry with the x, y, the x-axis, y-axis, and or the origin. So for this, what we're going to do is just check each of our cases, where for our first ones, it's pretty straightforward. If we want to check symmetry with the y-axis, what we're going to do is take our function y equals 1 minus x cubed, and I'm just going to leave a space in here to see if we end up with the same thing, and I'm going to plug in a negative x. So I would have in there y equals 1 minus a negative x cubed. Problem is negative x cubed, up to some problems with my equal sign there. That's going to end up having a triple negative, so it's going to stay negative and become 1 plus x cubed, and these are not quite the same. So I'm just going to use some bad notation and say they're not equal. We don't get what we want there, so we are not symmetric with respect to y. So I'm going to abbreviate that, not sim, with respect to WRT, the y-axis. Then for the x-axis, we're going to play a very similar game. I'm going to skip writing that same step at the front there, just to save myself a little bit of space because I realize I'm running low. And instead, we're going to, I don't know why that extra inflection there, but we're going to throw in a negative y is equal to 1 minus x cubed, and then we're just going to, well, factor the negative back over. Y equals x cubed minus 1, which, yes, it can get pretty close to the one we have at certain values for x, but in general, this is not the same as 1 minus x cubed, and so, just like before, we do not have symmetry with respect to the x-axis. So we are 0 for 2 so far, and then for our last check, we're going to see if we have symmetry with the origin, in which case we're going to replace both y and x. You can probably guess how this is going to go, but it's worth checking just to be sure. That will plug in negative y equals 1 minus negative x cubed, and you pull that through. You throw over the negative as well, and what you're going to end up with is y equals negative 1 minus x cubed. I have to save space there. Sorry if you're not quite on all the details, but the point is this is definitely not 1 minus x cubed in general, and so, like I said, I have to save a bit of space. We don't have symmetry with origin. Oh boy, my M's. Symmetric with respect to the origin. And yeah, sorry about The angle here is throwing off my penmanship even worse than it is usual, but you get the idea that we don't have what we want. And if you want to check this to be even more sure, you could throw together a quick graph of the function and see that it's pretty close to being symmetric with the origin, but it's just not quite there. If we have something that's called a perfectly odd function, which is what we're going to be talking about in a little bit, that would work. But before we get to that idea, before we get to even and odd functions, I do want to take a moment to look a bit far ahead, I guess. This is well outside the scope of our class, but it's worth talking about the idea that symmetry, even though it's pretty basic and geometric in how we interpret it here, actually hides a great deal of depth in terms of how we can get these copies of things with some adjustment, where the idea of copying is a transformation that's generally, in terms of a broader context, called an isometry. And in turn, an isometry describes any sort of movement of an object in some way or another that preserves the sense of distance it was originally defined with, which might not seem like a whole lot, but that is the cornerstone of a very, very far down the line mathematical subject called topology, which can be used to do some very, very strange things. It's a very deep and interesting topic, but for now, like I said, let's talk about function parity.